Hello student, welcome to our last lesson. In this lesson, we are going to look at boiling and melting. We first of all look at factors affecting melting and boiling, and there are two of them. One is pressure and number two is impurities. Then we look at the effect of pressure on melting point. We know that increase in pressure lowers the melting point of a substance. So when you increase the pressure, it will lower the melting point. But this one can be explained using the setup that we have here. We have two wooden support here. We have an ice block, and this ice block, we want to cut it using a wire. And this wire, we have put some weight here. What will happen? It is observed that the wire cuts its way through the ice block but leaves it as one piece. In other words, the ice block is left intact. What is happening? Explanation. Now, due to the hanging weight, these ones, the wire exerts pressure. You know that pressure is equal to force per unit area. The pressure on the ice beneath is under pressure, and therefore it melts at a temperature lower than its melting point. The water formed by melted ice overflows over the wire and immediately solidifies. And during this process of solidification, it gives out latent heat of fusion. And that heat is now absorbed by the wire or the copper wire, and it uses that heat to melt the ice below it. So the application of pressure on ice lowers the melting point at this particular point. That is why now the ice beneath the wire is melting, but as it flows over it, it is solidifying. So at the end, you will find that the wire will go through the ice, but the ice will remain intact. Then from there, we need to ask ourselves, why are we using copper wire? One, it's because it's a good conductor of heat. And number two, it has higher thermal conductivity than other metals. From there, we can move to applications of effects of pressure on melting point of ice. We have seen people who are skating. If you check their shoes, you will find that they are sharp. They have some spikes. And those spikes are the ones that are in contact with the ground or with the ice. So what is happening is that the weight of the skater is acting as the force. And the thin braids of the skater shoes are providing the area of contact. So because the area of contact is small, then you find that there will be a higher pressure, which implies that the higher pressure that is exerted is making the ice to form a film of water on which the skaters rides. So in other words, by application of that higher pressure, the melting point of ice is lowered and it melts at a lower temperature than its melting point. And therefore, the skater is able to slide. Then, this application can also be used in joining two ice cubes under pressure, where now you apply the pressure. As you apply the pressure, you'll find that you will lower the melting point, and as you lower the melting point, the ice cubes will melt at that particular point where you are applying pressure, and finally they will join together because that water will solidify. The effects of impurities on melting point. Impurities lowers the melting point of substances, and this one is applied in humid areas during winter, in which salt is spread on roads and paths to prevent freezing. By application of salt, you are adding impurities, and this will lower the freezing or the melting point. Then from there, we have the effects of impurities on boiling point. Now, impurities raise boiling point of substances, and that is why salted food cooks faster than unsalted one. Consider the setup that we have here below. We have water, that is distilled water here, in salt solution. Then we have the wire gauze, we have the source of heat, we have thermometers, and both of them are beakers. So we want to see which thermometer will record high temperature. And we have this as our explanation. When the liquids are heated to boiling, the boiling point of salt solution is observed to be higher than that of distilled water. And this is because when you put salt, that is an impurity. and therefore impurities raise the boiling point of that liquid. Then we look at the effect of pressure on boiling point. Decrease in pressure lowers the boiling point of a liquid, while increase in pressure raises the boiling point. That's why food takes longer to cook at higher altitude. At higher altitude, we have higher pressure than at lower altitude because pressure at higher altitude is higher. Then, it is also the reason why water in a sufuria closed with a lid boils faster than the one that is open. The steam pressure in a closed sufuria is higher, and this raises the boiling point of water, making it to boil faster. That is the reason we are saying that as you close the sufuria, what you are doing is that you are increasing the pressure. And as you increase the pressure, you raise the boiling point. Then we look at the pressure cooker. A pressure cooker is made up of strong-walled aluminum container fitted with a lid having a rubber sealing ring, as shown in this diagram. These are strong aluminum, this part. Then we have a cover. We have a pressure regulator, a vent, the overflow, or this is where if the pressure is so much, then it can be exited from this other side. Then we have the sealing ring, the rubber ring that we are talking about. Then we have air vent, lock pin, and these one are plastic handles, or the handles that are not good conductors of heat, so that you can use them. How does it work? The variable loading pin valve sets the pressure at which the steam is allowed to escape. That is, if the higher pressure is required, more loading is provided. The pressure builds up inside the pressure cooker. The pressure builds up to about 2.0 times 10 to the power 5 pascals. And at this point, it implies that the water will boil at 120 degrees Celsius. And this temperature is the one that will enhance rapid cooking of food that is inside the pressure or inside the pressure cooker. So what is important to note is that the pressure is building up. As the pressure is building up, it is raising the boiling point. So you'll have high temperature. Therefore, the food that is inside will cook faster because we have high temperature. Then we come to evaporation. This is a process by which liquid changes to gas, and this one occurs at all temperatures. It has no fixed temperature. Factors affecting the rate of evaporation. One, we have the temperature. As you increase the temperature, the rate of evaporation increases. That is, the rate of evaporation increases with temperature. Since increase in temperature increases the kinetic energy of molecules, and therefore the surface molecules easily escape because they have gained a lot of kinetic energy. Then number two, we have the surface area. The rate of evaporation increases with the surface area because more molecules are exposed when surface area is large, as shown in this diagram. We have water in a basin A is wider, will evaporate faster than that one in B, which is thinner, because we are saying more molecules are exposed here, and therefore they will escape to the environment. Then drought. Here we have that when we have wind or drought, it increases the rate of evaporation since it sweeps away the evaporating molecules, clearing the way for more molecules to escape. So as you have wind here, the molecules will be cleared by the wind, and therefore more molecules will be exposed, and therefore more will evaporate. That way it will increase the rate of evaporation. And that is why clothes dry faster on a windy day. Then we have humidity. Increase in humidity lowers rate of evaporation. And that is why clothes take longer to dry on a humid day. When we talk of humid, we are talking about the higher levels of water content in the atmosphere. So if it is so cold and there is a lot of water in the atmosphere, then your clothes will take longer to dry. Then from there we have the effects of evaporation. One is that one feels cold when methylated spirit is applied on his head after shaving. This is because the evaporating spirit gets latent heat of vaporization from your body, and therefore it causes cooling. Then we have thin layer of frost forms around the outside of the test tube walls when air is blown through mentholated spirit in the tube. Again, this is because the evaporating spirit obtains the latent heat of vaporization from the walls of the tube, creating a cooling effect. In other words, we are saying whenever there is evaporation, there is a cooling effect. And we have given these two examples. You feel cold when a mentholated spirit is applied on your head, and also there is formation of frost around the test tube when we have that the mentholated spirit is blown in the tube. Again, we are saying mentholated spirit is taking latent heat of vaporization, and by taking it is creating a cooling effect. Then from there we have the differences between evaporation and boiling. One, evaporation takes place at all temperatures, while boiling it takes place at a fixed temperature. Then number two, it takes place, that is evaporation, place on the liquid surface only, on the surface of the liquid, but boiling takes place throughout the liquid. Then in here, evaporation, we are saying that decrease in atmospheric pressure increases the rate of evaporation, but decrease in atmospheric pressure lowers the boiling point. So those are the three differences between boiling and evaporation. Then we look at the application of cooling by evaporation. One, we have sweating. Evaporating sweat absorbs latent heat of vaporization from the body and therefore creating a cooling effect. That is when the temperatures are very high, you sweat so that you can create a cooling effect, because the sweat will absorb the latent heat of vaporization and that will cool your body. Then number two, we have cooling of water in a porous pot. Water seeping out of the porous or water seeping out of the pot through the pores evaporates from the surface of the pot, creating a cooling effect. And that is why water that is placed inside a porous pot becomes cold, because as the water molecules are escaping from the pores, then they take away the latent heat of vaporization and therefore they create a cooling effect. So in other words, we are saying evaporation causes a cooling effect. From there we have the number three, the refrigerator. And the refrigerator looks like this one. It is used to store food so that it can remain cold. How does it work? One, we need to know that it consists of a highly volatile liquid, a liquid that can change into vapor very fast. And the liquid is passing through the pipes. You can see the pipes here that are moving. You can see the direction of the liquid. So as this liquid evaporates, it takes the latent heat of vaporization from the content or from the food that is inside the fridge, and therefore that food will remain cold. We have in the condenser here, as you can see, we have the compressor and the condenser pipe. So the compressed vapor, we are compressing the vapor here. The compressed vapor that is passing through the condenser pipe gives up latent heat. It gives up latent heat to the cooling fins, and it so condenses. Remember, as it gives out heat, these cooling fins will take the heat and the heat will be lost to the surrounding. As you can see, this part is outside the fridge. So the capillary tube causes the pressure to build up in the condenser. You can see now the capillary tube, these ones that are moving and these ones. This one is the capillary tube. So it is causing the pressure to build up in the condenser so that the vapor changes to liquid. So as it enters the capillary tube, it is in liquid form. So as it enters this capillary tube, it is in liquid form. But in the freezing compartment, this part, this tube widens. As you can see, it is clear that it is widening. So as it widens, then the tube carrying it implies that as it widens, then the pressure is reduced. And as the pressure is reduced, the fluid suddenly evaporates. And as it evaporates, it takes the latent heat of vaporization from the compartment from here. It will take the latent heat of vaporization, and therefore it will cause the temperature in this compartment to be low or to go down. That way, the food that is inside there will be cold. So the pump removes the vapor into the lower coil outside the cabinet, where it is compressed and changed into liquid form, and the process continues. Because as it changes into liquid form, again, it will go through the capillary tube, and then it will enter the freezing compartment at a wider tube. Again, it will evaporate and take or absorb the latent heat of vaporization. That way, the food inside will remain cold. Then the evaporator and the condenser pipe, as we have seen in our diagram, are highly coiled, and this ensures that it increases the surface area for the absorption and loss of heat respectively. Then the pipes that are made of good conductor are used. We are talking of the copper pipes, and these will increase heat conductivity. Then the copper fins enhances heat loss to the surrounding at the condenser pipe. Remember, the condenser is giving out heat, and then the copper fins are taking heat and then losing them to, or losing that heat energy to the surrounding. Then the refrigerator is sealed with double walls, and those double walls are filled with polystyrene. And this one ensures that there is no gain of heat from the outside, or there is no loss of heat from the outside. So the heat that is either lost, it is lost through the liquid vapor that is inside our pipe, the volatile liquid that is being used. So that way, we are able to ensure that the food inside the refrigerator remains cold. There is also a thermostat, and this will control the rate of evaporation. And if the rate of evaporation is controlled, then it implies that the temperature inside the refrigerator is also controlled. So that way, the refrigerator is working effectively. So after that, we have the assignment. Again, it is testing what we have just covered. So attempt the assignment and also prepare for the end of topic exam. Thank you, and let us meet in another topic.